Okay, so an AC machine now is where we apply a AC voltage to the motor and get it to run. Now, AC machines are more efficient than the DC machines or DC motors that we had before. So the key to AC machines is that we want to create a rotating magnetic field as part of the stator. There's two parts to achieve this. The first part is having a three-phase voltage source. And so that's what we're going to be talking about right now is three-phase voltage sources. So here's a basic picture of a three-phase voltage source. So you can kind of see that we basically have these three independent voltage sources that are all connected in what's called a Y configuration. We also have a load that's configured in a Y configuration where each of the loads have the same impedance. Now on our voltage sources, we see that here are the phasor voltage sources, and they each have the same amplitude, but they're different in phase. So the first one is going to have a 0 phase, the other one's going to be shifted 120 degrees one way and 120 degrees the other way to create these voltage sources. Now we're interested in finding the voltage at this center point here relative to this one. So we're going to come in here and make this one the ground and solve for the voltage on this side here. So the interesting thing, first of all, to look at this part here is we want to, why are these chosen this direction? So what ends up happening is with our three phases, we see that we have one voltage going up, and then we go over 120 degrees and then over 120 degrees. So you see that this is going, except for let's draw it this way. So this is our 0 degrees. We go positive 120, and then we go around this way 120. So if we take all of these and sum these voltages together, kind of put them end on end, you see that I have a voltage this way, and then we have a voltage this way, and then a voltage that way. So if we add them up as vectors, you see that VAN plus VBN plus VCN is equal to 0. So those phases are chosen specifically such that they all sum to 0. Okay, so now we want to look at the voltages. So we have make sure we get all this right. So the negative is connected in. So we're specifying this point as ground. This is my VAN. This is my VBN. This is my VCN. And then we're going to come over here and we're just going to draw them as resistors. And then we see that this point is connected over to here. This point here is connected over to here. Okay, and then this point here is our Vn that we're trying to find. So we're just going to do node voltage. And so each of these have a value of R. And so if I come up here, we're going to start with this node and we're going to go Vn minus VAN over R plus Vn minus VBN over R plus Vn minus VCN over R equals 0. We plug all these together and I get Vn times 1 over R plus 1 over R plus 1 over R equals VAN plus VBN plus VCN times 1 over r. Now, but we see right here that this part, all of this right here, is equal to 0. So we see that Vn times 3 over r is equal to 0, or Vn is equal to 0. So we see this is basically, we can see that we have that point is the same thing. If I put a ground there, it's not going to change anything. If I connect a line between the two, there's going to be no current through the line because all of these, this point, if it's balanced, is at the same voltage as that point. Now we also want to look at these currents, so we call this IA, and we see that if this point here is ground, then IA is going to be equal to VAN over R. The IB, which is right here, is going to be VBN over R, and then the same thing with our IC down here. IC is equal to VCN over R. Now this is all valid as long as we have a balanced load. So all of these loads have to be the same, and all of these voltage sources have to have the same magnitude and shifted by 120 degrees. Okay, so that is our basic three-phase circuit. So now when we look at our per-phase circuit, like I showed before, there's if I take and connect a line across here, which is called our neutral line, it's going to have no current. So if everything is perfectly balanced, if I have a wire here or not, doesn't really matter. But because of that, I can analyze a three-phase circuit by looking at a per-phase circuit. So you see this right here is equal to this part right here. And then I could just analyze this and get everything to work because of this hypothetical ground point here. The other thing that we want to do is we want to look at line-to-line voltages. So most power lines are transmitting three-phase circuits. And you can kind of see that here is our A line, our B line, and our C line. So that's these three lines going up. They usually have a communication or ground line up at the top that we don't really worry about. But you see with this line-to-line, we don't really have access to the neutral line. So typically when we're going to measure things, I'm going to measure the voltage between two lines. So it's the voltage, the line-to-line voltage is what you typically are able to measure much easier. So if I look at measuring the line-to-line voltage, I'm measuring from VA all the way down here to VB. So VAB is going to be VA minus VB. If we go through some algebra, we see that that's going to be the square root of 3 times larger than the line to neutral voltage. So you see right here that the line-to-line voltage is going to be the square root of 3 larger, and then it's going to be shifted by 30 degrees. What we care about the most is this square root of 3. So if I measure the line-to-line voltage, but I want the line to neutral or the phase voltage, I have to take my line-to-line and divide it by the square root of 3. Okay, now we want to look a little bit about voltages and powers as a function of time. So let's go over to MATLAB and kind of plot to see what these look like. So I already have here, so here is a time vector for doing 2 oscillations. I put in a VA, I'm using 240 volts. And then VB, you see, has this extra minus 120 degrees. And then the VC has the minus 240, which is the same thing as the plus 120. So the first thing that I want to do, and then I just chose a resistor of 10 ohms. And then the currents are just going to be these voltages divided by the resistor. So the first thing that we want to do is plot to see what these look like. So we're going to do plot T, and we're going to look at just our VA first. So we come over here, make this a little bigger so it's easier to see. Okay, so here is my VA voltage. Now we're going to plot my VB. And you see here's my VA going up, and then the VB is just shifted. So you see it has a shifted version of this. And then we can go ahead and plot our VC. And you see, it's going to be shifted again. So we can look at the sum of the two, of the three. And you see, like we showed before, they're going to be zeros. You can kind of see at this first point, I have like a plus about 300, a minus about 300, so those sum to 0. I pick another point. This one's like 350, and then I have 2 of the 175s, and so you see it always kind of sums to 0. Now we want to do the same thing for our instantaneous power. So we're going to multiply this times the IA. And you see here is the instantaneous power. It's basically just a sine squared. So the power is fluctuating up and down because it's an AC signal. And then I do the same thing for my B and the same thing for my C. And you see I get these sinusoidal varying powers, and they're all shifted like I would expect. And then when I add all of these together, now you see that even though the individual phases fluctuate in instantaneous power, they always add to a flat power. So when you're transmitting three-phase power, the amount of power that you're transmitting is continuous, even though you have these sinusoidally varying powers. So this kind of summarizes three-phase voltages. So just to review, we basically have okay, so just to review with our three-phase power, all the voltages are out of phase by, let me write these down. So we see that they're all shifted by 120 degrees. Okay, the V line to line magnitude is going to be equal to the square root of 3 times the V line to neutral. Okay, and the total power is constant. Okay, and then that finishes up our fast instruction on three-phase power.